So this is the lecture for September 3rd, and we're going to be looking into matter, atoms, and density. So matter is anything that takes up space. Air is invisible. If I look at what I'm holding in my hands, most people will say I'm holding nothing, but in fact I am holding air. Air has little different atoms. We know air is made out of nitrogen, oxygen, carbon dioxide. There's some other pollutants that are around, but air is full of tiny little particles. Matter could be the chair or the bed that you're sitting on. Matter is anything that takes up space or volume. So even liquids like water and sodas, those would still be matter. Now we know that we have three main states of matter. We have a solid, a liquid, and a gas. Those are our three main states. There is a fourth, plasma. They like to give example of lightning. A lightning strike would be an example of plasma. You also have plasma in your bloodstream. Plasma is just a charged liquid type substance. But solid is something where all the atoms or particles or molecules are packed so tightly together that it cannot be moved. It's like this pen. It's solid. There's nothing I can really change. I could break it, yes, but there's still these solid pieces. Liquid, on the other hand, will take up a little bit further apart. There's a little bit more space in between them. Gas has to be in a closed system. These particles are going to be so far apart from each other, and they're going to be bouncing off the walls, and they fit whatever container they are in. And again, plasma is very close to liquid, but it's just charged. And I'm drawing little lightning strikes for our plasma. But we have three main states of matter: solid, liquid, and gas. When we have a chart, there will be several different versions. You can start off with a solid, and then your liquid, and lastly your gas. If you are transitioning from a solid to a liquid, that process is going to be referred to as melting. And I'm going to underline this with green. If you are going from a liquid to a gas, you're going to be evaporating. If you want to work backwards, go from a gas to a liquid, that would be called condensing. That's where condensation comes from. If I have a glass of ice water, so here's my water with some ice cubes, and I have liquid forming on the outside of my glass. And sometimes the water will run down. That is your condensation. That's a form of condensing. The gas molecules around are being affected by the temperature of the ice, and so the air around the glass would start to go back to a liquid form. If we're going from a liquid to a solid, that would be referred to as freezing. So this would be our transitions between solids, liquids, and gases. As we learn more about matter, we're going to look more into what atoms are. Atoms are going to be unique for each element. And if it's not already on your Google Classroom, it will be here soon enough. We have what is called a periodic table. And the periodic table of elements will look something like this. You're going to have to excuse right now the stuff that's written off to the side. Earlier today in our chemistry class, we were looking at some of this. But we have lithium atoms, iron atoms, oxygen atoms. Atoms are unique to each individual element. And that is because of our protons. Protons are going to be positively charged. Now, within an atom, we also have neutrons and electrons. Neutrons will have no charge whatsoever. Electrons will be negatively charged. Now, we do have a symbol. Protons are a P with a little positive next to it. Neutrons are a little N with a 0. And electrons are a little E with a dash. So we have our protons, our neutrons, and our electrons. Protons and neutrons are going to be located in the nucleus. So protons and neutrons are in our nucleus. Electrons are going to be in what's called our electron cloud. So I'm going to have my nucleus here in the center. And then I will have an orbit where our electrons are located. That would be our electron cloud, where our orbits are. And this is our basic outline for an atom. That's one of our more current ones that was designed by Niels Bohr. So as we continue on, let's actually look at the history of our atom model. We started off way back when with the Greeks with an individual called Democritus. And he came up with the idea that an atom, or what they would call atomos, is something that can no longer be divided. And generally what they had was just a regular piece of paper or a plant, and they would be able to tear it apart. And eventually, as it was being torn apart, eventually it just became smaller and smaller to where you couldn't tear it apart anymore. And of course, as it gets smaller, there you go, you can't really see it as much. And so what they did was, eventually there must be a part where we can no longer take something apart. So atomos is actually a Greek word for indivisible, meaning cannot be taken apart. So Democritus came up with the idea for atoms. Didn't really give us a model. It wasn't until the 17th century that we had Mr. Dalton that gave us the idea that atoms must be in a spherical shape. Our next model only came about 20 years later with J.J. Thomson. His model decided that there was just positive and negative charges just kind of floating around within our circle, within our sphere. And about 9 years later, we had Charles Rutherford, who said our charges are going to be stuck in a center while other parts of our atom will take up the empty space around. When we came to Niels Bohr, this is where we start seeing those energy levels. We had our electrons, and our protons and our neutrons were in the center. Bohr came up with the idea that electrons are going to be on set paths, set orbitals, and those different orbitals will have different energy levels. The most common model that we see is really going to be Rutherford. Another version of Rutherford's atom kind of looks like this. Bohr models, we actually use this quite a bit in physical science later on. But our most up-to-date version is going to be made by Schrödinger. This was made in 1926. And this is by Schrödinger. And this is just a probability. We have our solid center where our electrons like to stay. And he liked to say that everything is a probability. And so where there's more dots, there's more chances of finding your electrons. And as you go out, there's going to be less dots where there's a less chance of finding those electrons. So everything has been built on over the years. I can tell you right now that you're going to want to have this written down, because I can guarantee you on a quiz, I will be asking you about the history of the atom models. So as we go on, we're going to start looking at density. Density is going to be defined by the equation density is equal to mass divided by volume. Density, mass, and volume. Mass is something that has a weight to it. When we think of weight, we can think of pounds, we can think of grams, kilograms, etc. Volume, as we know, is something that will take up space. And this can either be liquids or gases, but when we're looking at density, we are specifically looking at liquids. and not gases. So I'm going to put in parentheses, we're looking at liquid volume. And this will be taken in either milliliters or centimeters cubed. And I'll go ahead, I'll write this up here at the very, very top. If you have 1 milliliter, it'll be equal to 1 centimeter cubed. So if you're ever given a problem saying that, oh, I have 10 centimeters cubed, well then you have 10 milliliters. It's a nice 1-to-1 ratio. So if we're looking at our units, density will generally either be in kilograms or grams over milliliters. And I will be asking some basic questions within the work today to calculate density. So I'm going to take a little example here. I have a cube, and it's filled to the brim with particles, and it has a weight of 15 grams. I'm going to then put it into a beaker that is full of water. Water likes to have a density of 1 gram per milliliter. So this weight, with it being a nice solid 15 grams and it's very dense on the inside, we know that this particular box will sink. It's almost like a rock. A rock in water, it sinks. So when we calculate this, we're going to need to figure out how much water was actually displaced. So I'm going to go ahead and tell you that 3 milliliters of water was displaced. And we would simply calculate 15 divided by 3. We know that our units would be in grams per milliliter. 15 divided by 3 should be 5. So for our assignment today, there is a lab in Google Classroom. There is a link within the assignment. If you have any questions on how to access it or if something's not working quite right, please let me know and I will help you. If there's anything else, let me know.